to Politecnico Milano, to the Department of Aerospace Science and Technology. My name is Alberto Guardone. I'm the deputy head of the department, and I would like to welcome you and to welcome our guest. It's really a pleasure and an honor to have such a distinguished guest here, telling us some tales concerning one of the most inspiring adventures of last century. The Department of Aerospace Science and Technology is the only department in Italy fully devoted to the study of science and technology for aircraft, helicopters, and spacecraft. We are 50 professors and quite a large number of students now. We have 600 new bachelors every year and more than 300 graduates. We as engineers, we are used to design well in advance what is going to happen to our tools and to our machines, and usually we leave the role of the heroes to pilots or astronauts. That's a fortunate case we have here, that we have an engineer that is worked ahead of the mission and was had the skills and the capability to work during the mission and save the mission as astronauts usually do. The event is sponsored by by Politecnico, of course, by the Aerospace, by the Italian Association of Aerospace and of Aeronautic and Aerospace, IDA, and by the British Interplanetary Society. And I give the word to the British Interplanetary Society to present our guest. And I thank you again for being here, and thank you our guests for joining us.
Grazie, thank you. Thank you everybody for coming. So such a huge presence today, because it's really an important day for us and for me especially, and for Fabrizio Bernardini. Actually, I'm Dario Kubler. It's a dream that comes true, because I think such a big honor to be at the Politecnico, back after 30 plus years for me, and having such a great person today. Anyway, just quickly, I want to go through an introduction today. Don Eyles conference at the Politecnico Milano, and the title is Tales from the Lunar Module's Guidance Computer. I want just to highlight that within a few hours, 3:45 a.m., a great mission is going to leave the Earth from Guyana called Bepi Colombo. And this is a first mission that Europe is using to send a probe around Mercury, and it's a joint mission with Japan. And the name is based on a great man, great professor, and great mathematician from Padua University, Bepi Colombo. And I was honored to be there at this last conference a few months before he left for his journey to some other places. And Mr. Colombo was working 25 years with the European Space Agency, Italian Space Agency, and NASA. He is the one who was teaching NASA how to send a probe toward Mercury through Venice, using the gravitational force of other planets to slow down the mission. And Mariner 10 was his main mission, and he did a lot of things. But because of Don is here, I would like to highlight a few information he was teaching us during his last conference in 1983. So basically, he talked about the history of the space program, starting from the V1, V2, Peenemünde. Von Braun was the one who was building those rockets, and then moving up to Apollo missions and the space shuttle. And he was talking about the conquest of space in the future, moving through several steps. And we have the first part, it was mentioning the short term about meteorology and observation of the Earth. And it was mentioning that in a short time we will have a large telescope operating in the sky, the Hubble. He was involved on that mission as well. And then he says we will be able in a short time to listen to intelligent civilizations. We didn't yet, but we are very close because we know that there are other planets around other suns in the galaxy. And then he says it will be fundamental to develop new technologies using new materials in microgravity, and we did it. And he said we're going to build the ISS, International Space Station, and we did it. So everything he was predicting, it was coming true. And then he said in the long term, we are going to develop a cheaper transportation system after the space shuttle. And the space shuttle was already launching in the 80s. We know it's not true yet, but something is going to be true in a short time. And then he was talking about how to grab solar energy from space to use it on the ground, on the Earth, and to use the infinite minerals we can collect from other celestial bodies around the Earth and the solar system. And he also said this could happen only if the political conditions will allow this. He will say we have to remove the economic barriers. The barriers of thoughts and the barriers of freedom will be free to be used in this conquest. And if this going to happen, then we will have we will break the limits of the science fiction. And he says we will be able to move into space the most harmful activities that we don't want to do it on ground, on the Earth, to save the Earth, to save the climate on the Earth. And he was predicting those things because he says, and I need my glasses, otherwise I cannot read, that the united humanity could transform the Earth, our land, the jewel of the solar system, into a large protected garden in the short time of period. Oh, okay. So, this is British Interplanetary Society slogan, and we are glad to be here because BIS is also sponsoring this event, and BIS is going to give us some help to build something great. In particularly, in Italy there is a portion of BIS driven by my friend Fabrizio, and in Italy BIS is working heavily, especially in Rome, but we want to expand it also in Milan, so we are here to inform you that there is a possibility to become part of us, of BIS. And just to give you an example, you can see this project is a lunar lander that BIS designed in the 40s. So it was oops, technical problems. Oh, it's okay. So BIS was ahead of time on those kind of designs. BIS produced the first publication, the JBIS, the first academic journal devoted to astronautics, and is doing a lot of other things. And specifically in Italy, BIS in Rome, we are building simulators that are used just to allow the people to test how they can land on the moon, how can do rendezvous, how can they approach the ISS. Everything is done by the students in Roma. Here we are today to present you a fantastic project. This is the first step to celebrate the 50th anniversary of the Apollo landing. Tomorrow there will be the first celebration of Apollo 7 in Houston, and in December there will be Apollo 8, the first time the man left the Earth to go to reach the moon, and in July next year there will be the big celebration of Apollo 11. And we built a replica, and this is the first in the world, of the full Apollo guidance computer and the display and keyboard fully working, also thanks to the support of our friend Ronald Burki, who did a great job. He wrote the simulator of the Apollo software, and through that simulator we were able to build the replica, and what you see today here is the fully working original software of the Apollo guidance computer. So we are starting this Apollo 50 celebration. Actually, we started last week during the Maker Fair in Rome, and where we had the first presentation. We presented our jobs, we presented a lot of other things, very interesting. So I would encourage you to get in contact with the BIS. Today we are here to talk about specifically, and Don will do it, how the man could land on the moon. And he was going through several steps, and the programs were written by a guy. You can see his face here, and the software. And this gentleman, who was laureate on mathematics at the MIT of Boston, when he was 23 years old, he accepted the job at the instrumentation laboratories. And they asked him, you know, we have a job here for a guy who will have the responsibility to either land a man on the moon or crash a man on the moon. Do you want to do it? And he said, let me think, yes. And he is here, he did it. And then he worked on the Apollo program, on the space shuttle program, on the International Space Station program. So just 3 small jobs. Don, it was fantastic to have you here. So I want just to go through just a few comments that another great guy did it for him. This is a foreword of Sam Baston Luminary, the book that Don wrote, and it is from David Scott, commander of Apollo 15 mission. And it says, what's the most dangerous part of walking on the moon? And he answered, landing on the moon. And the lunar modules must slow down about 308,000 miles per hour to a level over 100 feet above an unknown surface, and descend through thick dust to a soft touchdown among craters, boulders, and rocks that have never seen before and never photographed. The margin of error is essentially nil. During the most critical phase of the landing, the lunar module must be controlled internally from 50,000 feet to touchdown through a single, very small, and very slow computer, using software programs that were written by hand by a single engineer. That software must be absolutely infallible. When the guidance software for the lunar landing was to be developed, this daunting task was assigned to an engineer who had no formal computer training, none was available. We're talking about 63, 65, 66, and who was only 23 years old. The software he wrote was part of a program called Luminary, and that engineer was Don Eyles. We have a small video now to remind you what happened in July.
No, non possiamo dire, non abbiamo l'audio.
Ah, we have no audio, so we can use this.
Ok, proviamo.
Try. Sorry, seems that technology didn't improve so much. Actually, I also did a mistake. Don Eyles, right?
Yes.
Because I used to say Don Eyles, Italian version, but your name is Don Eyles. Va bene, dai. Audio programs. In the meantime, you can see here the posters of my association ASIMOF from Varese, where we're building rockets and other stuff. Very cute, very cute. So if you want to know more, go to ASIMOF with the I think you need this.
We're going to show the video now. Switch to mute.
It's working. This is working. It's working. Risparmiamo il landing con Tito Stagno. C'è qualcuno che sa ballare, cantare, intrattenere il pubblico? Ballo attivissimo. C'è qualcuno che non crede che siamo andati sulla Luna? Sia chiaro, C'è qualcuno che ha fede in Microsoft?
A un certo punto un capriola viene della io mi ricordo l'emozioneria io ho capito quella
Ok, visto che i problemi tecnici sono un po' lunghi, buongiorno, io sono Paolo Attivissimo. Se qualcuno ha dei dubbi sullo sbarco sulla Luna chiedete a me, vi picchio, così lo vediamo subito. Ecco qua, grazie mille. Houston abbiamo un problema, la tecnologia corre ma non è affidabile come quella di Don Eyles, per cui vi intrattengo io come sostituto temporaneo intanto che la tecnologia di oggi viene incontro a noi. Vi racconto brevemente qui, visto? Solo in posizione delle mani è stato risolto tutto. Grazie.
Testing, am I hearable? Buonasera amici. My thanks to Dario and Fabrizio and my friends Luca Zanini and Barbara Ginfanti, who've all helped make this lovely trip to Italy possible. And my thanks to Professor Finzi and the distinguished faculty and to the many students who've come to hear me tonight. I'm going to show you a set of slides, sort of a show and tell. Very much the same presentation I've made several times to students at the Massachusetts Institute of Technology, where I was hired in 1966 to work on Apollo. Let's have the next slide. The story begins, I would say, with the man in this picture. That picture dates from probably 1963. That's Charles Stark Draper, the founder of the MIT Instrumentation Laboratory. He came across the country from California in 1922. He grew up in Windsor, Missouri, where as a teenager he was the town electrician. He got a psychology degree at Stanford. He came to Boston to investigate graduate schools. He was going to try out Harvard, but he never got there because he stopped at MIT, and he found that the MIT motto, mens et manus, mind and hand, suited him perfectly. And he went on to compile the longest transcript anyone ever had compiled at MIT at that time. He started developing instruments. He had his own airplane. He had failed to get into the Army Air Force, but he learned to fly anyway, and he used his own airplane to try out different instruments. He he developed ways of instrumenting an internal combustion engine to measure characteristics that had never been measured before, and went on from there. That led to accelerometers, which were able to sense and analyze the vibrations from the engine that allowed him to develop a detector that, that airplane pilots could use to keep the engines running smoothly. Go ahead. As the Second World War came upon us, he saw a way of applying his instrumentation to a problem that was of acute concern to the Navy, which was the protection of surface ships from air attack. And he developed the Mark 14 gun sight. He and his laboratory did. The Mark 14, that designation was imaginary. It was really a Mark 1. He said that he chose the number 14 to commemorate his infamous habit of holding on 14 at blackjack. And he thought if the instrument could succeed despite that handicap, he would have accomplished something. Next. And this is what happened, or this is where it led. That small picture is me at the same age. The bigger picture is the Battle of Santa Cruz Bay. The battleship in the far distance was equipped with this gun sight on its anti-aircraft artillery and was able to shoot down around 30 airplanes and to protect itself and the aircraft carrier in the foreground from attack. After the war, he was able to apply his instruments to a larger problem, the navigation in three-dimensional space. What we're seeing there is the installation of the first version of the Spire system, which I believe stands for Space Inertial Reference Equipment, which was a three-axis navigation instrument. He flew in that airplane to California to attend a conference on self-contained navigation systems. There were 12 people on the airplane. The pilot, Chip Collins, said to Doc, as we called him, this is an experimental aircraft. Should we really have so many people on board? And Draper's retort was, when you run a house of ill repute, you have to accept all comers. At any rate, they flew across the country guided by that unit. The pilot maintained altitude and ran the engines, but the steering was done by the automatic system. And when they got to LA, to Los Angeles, the error was only 10 miles. He listened to several speakers at the conference argue for why such a system was not possible. And then he sprung his trap, and he got up and marched to the front of the stage and said, well, I've just done it. Next. Moving on in history, of course, Sputnik was launched in 1957, and Yuri Gagarin flew in 1961. And that's a little bit out of place, actually, but those are two of the leading lights who were galvanized by Sputnik to start looking at the problems of a space mission. And the first that they considered was an unmanned mission to Mars. That work led, in Dick Batten's part, to the development of the first gravity assist trajectory for going to Mars by way of Venus. Hal Lanning, during that same era, developed the first compiler, the first computer language compiler, which of course revolutionized how you could code a computer. And those individuals were both on hand when I was working and both very available, and I sort of felt that they represented the two sides of the process. On Dr. Batten's part, he represented the legacy of Kepler and Newton and the equations we were using. Hal Lanning, the compiler language I just mentioned, but he was also responsible for the very simple but very effective operating system of the Apollo guidance computer. We saw the earlier version of Spire being installed in the B-29. That's the next version in the left photo, and that is Doc Draper explaining it to the reporter Eric Severide. You see how big it is. By the time of Apollo, on the right, that case is about 1 foot, about 1/3 of a meter in diameter. And its purpose, you can see the gimbal arrangement inside the case. The purpose was to allow that central component, which consists of 3 gyroscopes and 3 accelerometers, to hold its inertial position no matter how the spacecraft maneuvered around it. So the case moved, the central unit, which we call the stable member or the inertial platform, kept an inertial orientation. Moving on in history, Gagarin flew in '61, I believe, several orbits, and Alan Shepard in the left photo flew a short 15-minute mission. But emboldened by that, President Kennedy announced the Apollo project to go to the moon and back by the end of the decade, which set a very clear, substantial goal that eventually I helped achieve, along with a large number of other people. That is something we all know, how the Apollo spacecraft were packed into the pointed end of the Saturn V rocket. Next. And that's a sketch of the method of going to the moon, which of course involved a rendezvous in lunar orbit, which at the time was shockingly innovative, but it turned out to be the right way to do the mission. It reduced the size of the original rocket that had to be launched from Earth, and as we know, it worked out very well. And that's the trip back, which was involved the ascent stage of the LEM, rising again to lunar orbit, rendezvousing with the command module that took the crew home.
So we can say we really went to the moon?
I won't dignify that with an answer. Yes, we went to the moon. I try to leave that to people with more patience, such as Mr. Ativissimo, who's, I believe, in the audience, if I said your name right. One of the problems that had to be solved was human factors. And those sketches, those cartoons are from 1963, and they show the two extremes. The crew sitting doing nothing with nothing but a pull cord to request an abort, versus the crew being overly busy doing all sorts of things.
But they have the abort button, which is important for you.
We'll get back to that, yes, we will, on Apollo 14. And this illustrates how it turned out, at least with respect to the lunar landing. That's the LEM cockpit, of course, and during the lunar landing, or at least during the visibility part of the lunar landing, which I'll get to, the man in the left seat is the commander, and he's flying the spacecraft, which flies automatically until it gets down to around 7,000 feet. Meanwhile, the LEM pilot, sort of a misnomer on the right, is reading the displays from the display and keyboard unit. That's a picture of the real LEM cockpit, and I won't go through that in detail. You do see the telescope near the top center, which allowed the IMU, the inertial measurement unit, which we saw recently, allowed its alignment to be checked and to be changed as needed for the particular maneuver that was going to be attempted. That's personal. That's me in high school in 1957 approximately, and at the moment I was hired in 1966 to go to work on the project. The surprise was that in 1966 a great deal of the work for the command module had been accomplished, but the limb was just getting started, and I was one of the people who was lucky enough to be there at the right time to participate in that. The chap on the right, George Cherry, hired me. He was hiring practically anyone at that point. He said he had even hired literature majors. And I was assigned to work with Alan Klump on the left, who turned an equation that Cherry had developed into a practical system, which I helped implement in the guidance computer. That's the building we worked in. And there finally is the computer itself. It's 1 cubic foot. That's another story that goes back to Dick Batten, because at an early stage of the project, the engineers at North American Aircraft who built the command module said, well, you're going to have this computer, how big is it exactly? And Batten said, well, just tell them it's a cubic foot, which was a fairly daring thing to say, but in fact that is 1 cubic foot. The memory was a combination of a type of fixed memory called rope memory, of which there were 36K words. These words were 16-bit words, of which 15 bits were usable. The 16th was for error checking. This is one of those modules. This is 12 kilobytes of extremely reliable read-only memory, weighing perhaps a kilogram. The computer consumed, weighed 70 pounds, consumed 55 watts, and we'll talk a little more about it. Next slide. It was, one of the things it pioneered was the use of integrated circuits. And in fact, it was made up of 5,600 of the same logical unit, packaged 2 to each integrated circuit. It was a triple input NOR gate. And the lower illustration shows how the core rope memory worked. There were wires that passed through ferrite cores that were used to energize them. Each one then acted like a transformer. And the wires at the top either passed through or around these cores to represent ones and zeros. That shows the various interfaces of the computer, ranging from the ability to turn on and off the engines of the ascent and descent stage, the maneuvering jets, the disky and the other cockpit displays, and of course a link to the ground, hand controllers, 2 radars, one used for landing, the other for rendezvousing, and the telescope. And the limb itself, the sort of lower stage that's gold in the picture, contains the descent propulsion system and is left behind on the moon when the upper part separates and goes back to lunar orbit. And that's very similar to the illustration you saw earlier in the introduction that shows the phases of the lunar landing. There were 3. The first was the braking phase, the longest, over 500 seconds. It was mostly about shedding forward velocity. During that phase, the landing radar had to lock onto the surface because inertial guidance had gotten us that far, but it's not exact enough to actually land without a double check on the inertial navigation. So the radar gave us a reading of the speed across the surface and the altitude. And if that failed to lock on, the landing would have been impossible. At about 7,000 feet, and it varied from mission to mission, depending on how the targets were set up, a different set of target conditions was loaded into the computer with the result that the limb pitched forward, giving the astronauts a very good, clear view of the lunar surface in front of them. And there was a method during that phase when, in broad terms, the commander on the left, using marks on his window, could bend the trajectory towards what looked like a more hospitable area. And then finally, as planned, at an altitude of roughly 400 feet, but it was a question of individual choice, the commander took over control in a semi-manual mode, using which he flew the limb very much like a helicopter to choose the exact spot where he wanted to land. The targets for those different phases were important, so that the velocity shed during the braking phase allowed the limb to take that more upright posture. But the limb did maneuver continuously during that entire sequence. That's a picture of Hugh Blair Smith, who was instrumental in designing the languages we were using. Next. That's what we stared at when we wanted to think about the code. If you're imagining monitors of any kind on our desk, you're wrong. We didn't have those. We looked at paper, and there was a certain advantage to that. That's a book of paper about 6 inches thick, but it contains the entire program, the entire 3,600 words of memory, and you knew that the answer was in there. You know, it was contained. You could get your mind around it. Unlike these days where you may have millions of lines of code and no single person could understand that to, you know, down to the last degree, but at least the answer was in there, and if you were clever, you could find it. It was not always easy to read, but the assembler developed by Hugh Blair Smith, who you just saw, did have tools like symbol tables that allowed you to navigate around the document. Also in that picture is the coding form we used, also a copy of the memo, an unpretentious memo that we call Memo 9 that described the assembler language, the language readable by the machine. Next.
No. And the Coke?
Oh, and the Coke was my own personal beverage fuel of choice when I was doing that work. This page has examples of the 2 languages we used. I just mentioned the assembler language. There is also, on the bottom half of that page, a language that we called interpretive. We call the assembler language BASIC, by the way, but it has no relation to any other language named BASIC. It was very much custom for this machine, although some of the instructions actually harked back to a computer called Whirlwind, which was a large vacuum tube computer developed at MIT, originally with flight simulation in mind, and several of the technologies developed there, although obviously not vacuum tubes, fed into the Apollo computer. As I was about to say, the bottom of the page is our interpretive language, a language that ran much slower. Really what those codes that you see there did was invoke some subroutines to do various tasks, mostly associated with the sort of vector matrix arithmetic that you needed to do to navigate in 3 space. And that's where our hands touch the clay. That's a IBM Model 26 key punch machine, because when we wrote code, we wrote it, well, first, if you chose to, on the coding forms, but then you transferred it to IBM punch cards using that machine, and those were fed to the assembler, and thus the program was developed through a large number of revisions. The genealogy of the program used in the limb to land on the moon went back into the early 60s. I can't recite it by heart, but the program used for the Limb 1 mission, an unmanned mission in early 68, was called Sunburst. And the mission, the rope, as we called it, referencing the core rope memory, the rope that flew Apollo 10 and all the landings was called Luminary. Luminary 99 flew Apollo 11. Development continued as we tried to improve the software's ability to help the man land on the moon. And the version of Luminary that flew the last 3 landings, 15, 16, and 17, was Luminary 210. Just to show you a few of the other personalities, on the upper left is Davey Hoag, who at the laboratory was in charge of the entire primary guidance system development, because we developed not only the code and the computer, but also the IMU and the associated systems. Upper right is another very important manager, Ralph Reagan, one of Doc Draper's deputies. Then below we have Eldon Hall on the left, who was the main designer of the computer hardware, and Norm Sears, who worked with Dick Batten and who's still a very good friend of mine. and a few others, Dana Dinsmore on the left, who did some of the system programming, and for a while was my girlfriend. Peter Adler, who handled what we call the P40s, the powered flight phases for orbital maneuvering and mid-course corrections. And on the right is Margaret Hamilton and Dan Likely, who in succession were managers of a part of the software effort. During that period, we were working with astronauts in Cambridge, Massachusetts. Alan Shepard is in both those pictures, and if you could see them big enough, you could recognize several other of the original famous astronauts. On the right-hand picture, that was Alan Shepard again and Buzz Aldrin behind him. Next. And this references the LEM 1 mission launched on a Saturn 1B. The LEM had no legs. It was delivered in that strange-looking aircraft called a Super Guppy. It was not, from my point of view, from our point of view, a really successful mission. A decision was made right before launch to delay the arming of the engine, the descent engine. There was concern about the valves and that propellant might enter the engine prematurely. And as a result, the engine arm signal, which, pressurized the tanks with helium. That's the blue part of that diagram, which I'm not obviously going to explain in detail. But the arming happened late, equivalent to activating the fuel pump late. As a result, the engine came up to thrust late, and a little piece of code that I wrote called the Delta V monitor thus concluded that the engine had failed and sent a shutdown signal. That meant that sort of, this was not the simulated landing burn. This was a simulation of the much shorter burn that in a real landing would have been used to lower the LEM's orbit to the one from which the landing half an orbit later could begin. NASA turned off the primary guidance system. They accomplished the other mission objectives, chiefly the tests of the different propulsion systems under ground control, and called the mission a success. But we sort of hung our heads, and the public reaction was that the computer had fouled up because it had sent this shutdown signal, even though it worked according to specification. And if the change in the procedures had not occurred, there would have been no problem. I finally got to see a launch. I say finally, it was actually pretty early on, and it may have been consolation to me for the fact that my code had been blamed unjustly for Apollo 5, for the LEM 1 mission. I was able to go to the Cape, to Cape Canaveral, to see the launch of the 502 mission. That was the second Saturn V. Oops, go back. Oh, yes. You're going the wrong direction. Sorry. There we are. Yeah, okay, at the switch. Anyway, that other picture, you may wonder why that's there, but I got back to my motel room that evening and turned on the television and learned that Martin Luther King had been assassinated the same day at the Lorraine Motel in Memphis, Tennessee. Those are the crews of the early missions, 7, 8, 9, and 10. Of course, we're about to have, I guess tomorrow, the anniversary of Apollo 7, commanded by Wally Schirra. After that came the famous Apollo 8 mission that actually went to lunar orbit with just the command module. Then Apollo 9, a mission with the LEM in Earth orbit, and Apollo 10, a mission with the LEM in lunar orbit. Next. And that's the mission profile, if you will, for Apollo 8. It was a shockingly bold decision, which some people attribute to the fact that there was concern that the Russians were going to one-up us by putting a man in lunar orbit. That turned out not to have been the case. And to my way of thinking, the real motivation for doing Apollo 8 in lunar orbit was to get early experience in operating in lunar orbit and also to encourage everyone, including me, to think that a landing in 1969 really would be possible. And of course, they created those famous photographs of an Earthrise over the moon horizon. Sometimes I throw in a picture just because I like it. That's from Apollo 9. That's the only time the LIM operated with a crew in Earth orbit. So that's the LIM photographed against the ocean of Earth. You may wonder how we tested the software, and this is one of the ways. That's our hybrid simulator in Cambridge. There's a cockpit on the left that we could use when we needed a man in the loop. It was called the hybrid simulation because it combined analog and digital computers. The analog computers, Beckman analogs, programmed with a plug board that resembled a mass of multicolored spaghetti, are visible, although that's a black and white photo, unfortunately. The upper right photo, you see there's a display and keyboard unit on the middle cabinet. A real Apollo guidance computer is inside that cabinet, concealed, and we could run tests from that location if we didn't need the manned operations. And to avoid having to manufacture rope memory every time we had a new version to test, there was something called the core rope simulator that could be fed with a tape that would emulate the fixed memory. Now we get into missions. Apollo 11, I tried to find interesting pictures of the crews. Some are more interesting than others. You can maybe see something about the personalities there. That was not a crew that was close to each other. Buzz Aldrin on the right, Mike Collins on the left, and of course Neil Armstrong in the middle. Very reticent, highly competent and brave individual. They all were brave. Next. And that's the rollout of Apollo 11, which gives you an idea of the magnificent launch facilities at Cape Canaveral that were created for Apollo. The rocket that's emerging from the big building is 360-something feet tall. It's riding a transporter that's very large, let us say, the size of a supermarket, except that supermarkets here are smaller. So it rides on tank treads, sort of, to the launch site, which is 3 miles away. And since we're talking about Apollo 11, it was a good time to sort of introduce the concept of the disky, which was our general purpose way of communicating in both directions between the crew and the computer. The crew could type in a verb and a noun. That was a system invented by a man named Ramon Alonso, Spaniard, who still lives in Cambridge. And the verb might be something like display, the verb 6 that you see in that picture. And the noun, in this case, identified what the data is in those 3 5-digit registers that you see. The astronauts in their training had to know what the data was for each noun, each important noun. They also had to know where the decimal point was. All the displays during the landing included the vital numbers of altitude and altitude rate. Altitude rate is the middle register. You see we're going down at 92.7 feet per second at an altitude of about 40,000 feet. It was soon after that the first alarm occurred. It occurred because Buzz Aldrin keyed in verb 16, noun 68 to look at data from the landing radar, and that created an extra load on the computer. And as a result of that, for a reason we did not understand at the time, the computer was overloaded. That's the display that Buzz keyed in to see what alarm code it was. That 1202 indicated that the queues used by the executive system were full. And that's a plot of the duty cycle during the landing. You can see that from the moment the engine was lit, in various steps, the amount of computation time needed by the program kept increasing to the point, the plateau there, where the margin was barely 10%. And as a result, we had those same alarms, or there were actually two similar types, occurred 5 times during the landing. And what happened when each of those occurred is represented by the right-hand picture. You see the consumption of queue space going up until the point where an alarm occurred. Each time the alarm occurred, the computer restarted on the fly, and the vital computations were reconstructed, and we were able to keep flying in Cambridge. If it had been left up to me, I probably would have asked for an abort, because something we didn't understand was happening in the computer. NASA knew better, I'm happy to say. They had been observing the system operating from the outside, and they knew that the LIM could still fly under this condition, and they weren't quite as concerned with what was actually happening inside. And if you want to know what the root of the problem was, it's in the lower left of that picture. That angle resolver, because of the fact that the cockpit switches were in a position that, unbeknownst to most people, created a condition where the resolver was being fed with contradictory information. It was as though it was trying to find an angle whose sine and cosine were both 0, and as a result was counting wildly, and each of those counts actually consumed a memory cycle in the computer, and there was enough of that counting going on to consume about 13% of the total CPU time, and with a margin that during the braking phase, when the extra display was called up, was less than 13%, and which during the visibility phase, that plateau you saw earlier, was about 10%. So there were 2 such alarms in the braking phase and 3 more during the visibility phase, but we kept flying. There were strange things that happened in the displays, but the guidance equation and the commands to the engine and to the attitude maneuvering all kept working, and we landed. Now, NASA set more ambitious goals. Thank you. He detected a frog in my throat there. That's the crew of Apollo 12, and that's a crew that did have a great rapport and were a lot of fun to boot. I attended the crew training meeting where it was our job to train the astronauts to operate our system on 11, which was a very formal meeting in Houston with managers present. Pete Conrad on the left, who I think of as a blend of Richard Widmark and Slim Pickens. He wanted to keep the managers away, so he chose to have that meeting at the Cape, in the crew training building at Cape Canaveral, and it made for a much more productive as well as much more fun session. But at any rate, that mission was set the goal of making a pinpoint landing, and that was symbolized by landing next to one of the Surveyor unmanned spacecraft that had previously landed, to land close enough to it to walk to it. And between Apollo 11 and Apollo 12, we did add some capability to the guidance computer, basically a new noun that allowed the landing site to be updated at the last minute. We didn't update the navigation, we updated the landing site because it was simpler, based on tracking information. Because as the LIM came around the moon the last time before the landing, that was an ideal situation for the ground tracking to locate the LIM and its speed. And this new capability we added allowed that information to be input during that brief period of time. Right after 11, really, after that goal had been set, Pete Conrad invited Alan Klump and I down to Cape Canaveral, I think to talk to him about what we could tell him about making this pinpoint landing, but I think also to let us see something from his point of view. And we got to know the simulator that's in this picture, which you could think of as NASA's equivalent to our own hybrid sim, except this one was very well done, especially in the area of the visual displays. It did not have a real AGC, but it was able to emulate the AGC fast enough to keep up with real time. And there's a color code there. The brown in the background is a command module simulator. The green is a limb. Deep inside that collection of boxes, John Young, the astronaut, called it the Great Train Wreck. It's about 30 feet high. Inside of that is a very realistic limb cockpit. And the purpose of the boxes clustered around it is to deliver the visual displays to the windows of the limb, the two big front windows and the small docking window that's overhead. And as I say, those displays are extremely good. They originated in that sort of canopy-like structure that's visible behind the front pile of boxes, if you will, that had a literal terrain model of the landing site area. And there was a camera that mimicked the movements of the limb, and the image taken from that camera was processed and projected in front of the windows of the limb in a way that was optically correct. And in fact, it was so good that it can be used for landing at a very specific spot on the moon. And on that visit, I had the fun of actually flying a few landing simulations with Pete Conrad. And the mission,
Example of virtual reality, right?
you could call it virtual reality, except that it was not all done with goggles. It was done with an actual hardware limb cockpit and displays delivered to the outside. When I say it was a very realistic limb cockpit, it was so realistic that it could support tests when the astronauts were wearing their suits. There was a way of plugging in and getting oxygen in your suit. Not that I ever flew it that way. But the mission was successful. That's Conrad next to the surveyor with the limb in the background. So moving on, the next mission, of course, was Apollo 13. And I imagine most of you have seen the movie or know something about that mission. Next. What happened was that there was an explosion in the service module, as you can see, blew the side off it, completely disabled the electrical generation capability of the command module. There was some question still whether or not the heat shield had been damaged. It could have been, for all we knew. The real heroes of this mission were, first of all, the mission planners on the ground who developed procedures for a situation that had never remotely been contemplated, the complete electrical death of the command module, in really a marathon effort, and the crew. And the movie, I think, exaggerates the explosion and the amount of movement during some of the maneuvers, but fails to capture what I think of as the real stress of that mission, the thing that made the crew heroes. As 3 men, it was 87 hours between the explosion and splashdown. During that time, 3 men who might already be dead, you could say, had to huddle together for warmth with condensed water dripping off the sides of the spacecraft, getting sicker and sicker, and having to execute these fairly complex procedures that were being developed on the ground. And that was success. That was because the resumption of communication after the reentry was delayed from where I was sitting in Cambridge. That picture was the first sign that, in fact, the crew had survived. I won't talk much about this, but one of the things that, because we were going so fast, we probably failed to notice sooner was the fact that there was a near instability in the descent engine throttle based on the fact, similar to Limb 1, where a decision had been made to arm, a decision had been made affecting the descent propulsion system that wasn't properly communicated. In this case, the manufacturer had improved the engine to the extent of making the throttle reaction time faster, but we were modeling the throttle reaction time, and as a result, we were overcompensating, and we were nearly in an unstable situation. And it took a number of months to figure out what the problem was. But fortunately, before Apollo 14, we did solve that. Or I should say Alan Klump did, because it was mostly him working on that. And then we come to Apollo 14, another one of those pictures that says something about the crew. You can see Alan Shepard, returned to flight status after a operation had been developed to cure his inner ear problem, and you see the deference of the other two crew members. That's Ed Mitchell on the left, who did ESP experiments on the way to the moon, on the way back from the moon. And that is the mission that brought me my own 15 minutes of fame, if you will, because it was discovered a few hours before the landing was to begin that there was a short circuit in the abort button. That was a button that would normally be used, or abnormally be used, to command an abort very quickly if something went wrong during the landing. But if it happened to short out during the landing erroneously, it would ruin the landing, because we would immediately turn around and go back to lunar orbit. So a way that left no window of vulnerability had to be developed to make the computer program ignore that switch. That turned out to hinge on setting a register inside the computer, because we had the ability through the diski to reach deep into the memory of the computer to set it erroneously to say that an abort was in progress, but then to do and get past the period of vulnerability and then clean up afterwards so that the landing could resume normally. It disabled the button, but an abort could still have been commanded through the keyboard. And in the course of a couple of hours, we developed that procedure and tested it. That, although it's probably not readable from where you're sitting, that's the actual page that contains the code that was involved. That's the procedure itself. The first step is to set the mode register to indicate an abort, and the other parts of the procedure you could call cleaning up afterwards. That's me being awarded a NASA Public Service Award in Houston. That's Alan Shepard shaking my hand. And the next slide is the team in Cambridge that were involved. You see Doc Draper next to me in the upper photo. The lower photo is sort of the inner group, if you will. Larry Berman, who handled the ascent and abort programs on the left, Peter Volanti, who was basically a rendezvous expert, in me, and behind Sam Drake, who was one of the experts in the hybrid simulation facility, and Bruce McCoy, a lower level manager who originally brought me the news that the problem had occurred. Some of the published accounts have a car rushing to my apartment, me throwing a robe on over my pajamas, and being rushed to the lab and told to solve this problem. Of course, that's absurd. I wouldn't have been sleeping with the lunar landing in process and about to be in progress. And I was in fact at the lab. I was in my office working on something else, waiting for the landing, when Bruce came to tell me that there'd been this problem, and that led to the whole effort.
And in any case, you're not using pajamas, right?
Yeah, no, I was not sleeping in pajamas at that point. And the idea of it being an Air Force car is also fairly absurd. And of me having a driveway on Beacon Hill in Boston was equally absurd. Actually, go back one. That's, we're coming now to Apollo 15, and it's sort of smooth sailing from now on. That's another astronaut, Dave Scott, in the middle, who I also flew a number of simulations with, and who was kind enough to write an introduction for my book, which you heard quoted earlier. Next. And that mission, another one of those pictures I quite like, and another example of innovation, if you will. You see Doc Draper at the center, and that's a good illustration of his persona, sort of the dapper ladies' man a little bit. And he's talking, that's in the press grandstand near the Vertical Assembly Building at the Cape. And he's talking to a reporter named Mary Bubb, who for every mission constructed a hat that translated the mission patch, shown in color, into 3 dimensions. You can sort of see the sort of chevron shapes up above a gray lunar dome representing the patch. That's the Apollo 15 liftoff, which I also saw, witnessed. I discovered that we were working on something at that point called erasable memory programs. As I said earlier, the same luminary flew 15, 16, and 17, so we weren't coding, writing hard code anymore, but we were writing a family of small bits of code, 50 lines or so, that could be used to handle certain malfunctions. By then, the crew was being quarantined in the period leading up to the launch, and no one except them was allowed into the simulator. But as soon as they left, as soon as they launched, simulator time became abundant. And so I developed the routine of going down to Florida the night before the launch, seeing the liftoff, and then spending 2 or 2.5 days very productively in the simulator, and then flying back to Cambridge, where I always was for the landing itself. That's the moon buggy that first flew on Apollo 15 that increased the range of the astronauts. And Apollo 15 is notable for finding that rock, nicknamed the Genesis rock, that is almost back to the original lunar crust. I think it's said to be 3.5 billion years old. It was the only substantial piece of material of that antiquity that any of the missions found. The left-hand picture taken from orbit much later actually shows the signs, shows the descent stage left behind, and the tracks made by the astronauts as they walked around. Apollo 16, John Young in the middle, who we used to call America's greatest astronaut, and it's not a bad label because he had a very long career going back to the Gemini program and extending deep into the shuttle era. He had a brilliant idea of a way to land the limb even more accurately using some of the capability that we already had. We got together on it. He told me his idea, which I liked immediately, and I was able, given there was no one who was going to say no to me, I was able to put together a version of the flight program with that new capability in it and took it back to the Cape, and we flew quite a large number of missions, of landings, I should say, using that capability. He said, it's the slickest thing I ever saw. That's the kind of thing he probably said quite a few times to different people, but it was slick. But it involved a fairly deep change to the program, and so it was not adopted. But we certainly had fun doing it. That's Apollo 16 on the moon. Go ahead. And we come to the last landing mission, Apollo 17, with Gene Cernan sitting, and Harrison Schmitt at the upper left, the only true scientist that we sent to the moon. Although I later talked to a geologist, Farouk Elbaz, who said that actually the astronauts were better collectors of samples than Schmitt was because he thought too much. He was too well educated to have done as good a job. Next. I was also, as I said, I went to the launches for 15, 16, and 17. The launch of Apollo 17 was at night, and that picture, which I found, is the best representation of what it was like, the way the sort of dense Florida atmosphere, misty atmosphere, was lit up orange everywhere you looked, from horizon to horizon by the flame of the rocket. And that's my